unique. After that, we will look at different use cases, how to build them, what harvester storage could you use, and also what do you need to build your own device. As Thierry mentioned, for any question, do not hesitate to use the chat, and I will be glad to answer all your questions during the Q&A session. So who is EPEAS? EPEAS has been created 5 years ago based on more than 10 years of research at the UCL University in Belgium. And this research was about low power IC design. We decided to use this knowledge in the first product family dedicated for energy harvesting, and we will cover those products today and learn a bit more about them. We have offices in Belgium, but also in Switzerland and quite recently in the USA. We have a worldwide distribution, so please do not hesitate to ask if you are interested in any evaluation kit or IC in the AEM family. So while looking at energy harvesting as the first family of product, the number of electronic devices increases every day. We are now surrounded by a lot of connecting devices, tracking devices, sensing devices. We can find application in the industrial world. We can see application in what's called smart home. We have a lot of examples in different markets, but unfortunately, most of those devices are powered by disposable battery. That reduce first the energy available, since we always want to increase the number of features, but also we want to extend the lifetime. And it also implies some maintenance cost and logistic issue, which is providing edge to the industry and or the end user, how to estimate the real lifetime, how to integrate the temperature influence, who is going to change the battery, how much is it going to cost. And all those problems could go away using energy harvesting, using the ambient energy you have around the device to supply it. How energy harvesting does it work? What is it? It's actually a new way of supplying your electronic. Instead of using a disposable battery, you use a rechargeable storage element, which is recharged by the ambient sources. We can see here the light, a difference of temperature, some movement, vibration, or RF signal. RF signal is a bit apart, since for the moment, we strongly recommend to use a dedicated emitter, but it depends on the environment. If you have energy, RF energy available, we could use it as a source, and we will see an example a bit later. So what do you need to harvest energy? First, you need an harvester, which will actually transform the energy into electrical power. The harvester will be different for the different sources. The most known is the light using photovoltaic cell. For a difference of temperature, we could use thermoelectric generator, which is actually using the Seebeck effect to transform the difference of temperature into electrical power. Vibration or any low frequency signal, you can use a mechanical generator. There are actually different technology there. And for RF signal, you will use an antenna as the harvester. So in addition to this harvester, you need a storage element. There you have two big technology. First one being the rechargeable battery and supercapacitor. You might be wondering why you need something between the harvester and the storage element. First, because you would like to extract the maximum power. You would like to be sure that since we are dealing with low power, you are really taking the maximum and all the available power to store it in the storage element. You would like also to get started, to cold start from low voltage and low power. We also would like to protect the storage elements, so taking care of those rechargeable storage to avoid destroying them or making their life smaller because we went above the maximum voltage. And we would like to directly supply an hardware device, an application, some radio sensor to build the complete application. And all those functions are integrated in the AEM, standing for Ambient Energy Manager. But how to extract and how to be sure that we extract the maximum power? How do we do that? If we look at an example being the PV curve, so power versus voltage curve here in green of a photovoltaic cell, you see the current curve. If we look at the same PV cell below a higher luminosity, what you see is that you have a maximum power point, which is called VMPP. And this maximum power point actually is achieved by working at a defined voltage VMPP here. So what we want to do is working at that voltage to ensure that we are really transferring the maximum power from the harvester to the storage through the AEM. This is achieved by having an MPPT tracking feature and maximum power point tracking feature. We also discussed in the previous slide that we would like to cold start, so starting with a very low voltage below half a volt, and we would like also, even if we have low power, like some microwatt, to get started and start extracting the energy. The MPPT, so maximum power point tracking feature, how does it work? It works by measuring the open circuit voltage, here you see VOC, and applying a certain ratio. And this ratio is actually a constant, and it's directly related to the technology, the harvester technology. So this ratio, and we will see some example, is provided in the harvester datasheet, and it will be different for the different harvester because they will have different behavior. But anyway, you will find this ratio somewhere in the harvester datasheet, and you will have to configure the AEM to give him this ratio. So what will do the AEM? It will at a constant frequency get disconnected from the harvester during 1% of the time, get reconnected, measure the open circuit, apply the ratio, and define its new working voltage. So at a constant frequency, we will adapt the working voltage to ensure you that even if the environment changes, we will be at the maximum power point. We just mentioned that you can configure the AEM. All those configuration is done by IO pins, so you have no software, you don't need any software connection or anything else. You just have to define 7 IO pins to define the MPP ratio, and as we will see a bit later, you can also define the level to protect your storage element. But this is really an hardware product. If we look at the AEM inside the system, so with the harvester and the storage, we can see that the AEM will actually get the energy from the harvester. It will have some internal losses being 400 nanoamps, and it will manage it to the storage. We have some condition to get started. So as we mentioned, the cold start feature, which are 3 microwatt and 380 millivolt. That's the condition we need at the AEM input to get the AEM starting and extracting the energy. We have the MPPT feature, we have the protection of the storage element, and we provide 2 regulated output, 2 regulated voltages, HV out, LV out, coming from internal converter, linear converter. The maximum input range are 5 volt for the voltage and 110 milliamps for the current. We have an additional feature, you have the option to connect a primary battery. Actually, you can connect any storage, but we will use it as a backup source solution. So if the storage is being discharged and reaching its minimum voltage, we will use the primary battery to get the storage back again to a certain level, and then we will switch back from the primary to the source to see if we have some energy back at the source. But what makes the AEM unique? First key feature is the lowest power cold start. So you only need 3 microwatt to get started. That's actually the lowest power required on the market. The internal boost converter, so converting the voltage from low voltage at the source to the storage element, is working from 50 millivolt to 5 volt. Those 50 millivolt is after cold starting. So we need 380 millivolt, 3 microwatt to get started. And as soon as we have cold started, the internal boost will work from 50 millivolt to 5 volt. We mentioned the lowest power cold start, which is actually achieved because we have a really low quiescent current, about 400 nanoamps. This is a global one. Since you don't need any resistor or anything to configure the AEM, it's just IOP. This is the global leakage you have for your system. And we have the smallest bond. Not the smallest package, but you just need 7 passive around, 2 inductor and 5 capacitor, which is actually fitting in 1 centimeter square. As further feature, we have the primary battery option we just discussed. We also have some additional feature being called BAL, for a balancing circuit used mostly for supercapacitor, dual cell supercapacitor. And we also integrate a new feature called constant impedance, ZMPP, which is actually dedicated for thermal sources, since the TG, so the thermoelectric generator used to transform thermal energy into electric one, most of the time the manufacturer will characterize by its impedance. So you don't have a voltage ratio like we saw on the curve. You don't have that ratio in the datasheet. You have the optimal impedance, and you can define it with using the features at MPB. We mentioned that you can define different protection level on the storage element, giving you flexibility to use any kind of storage technology, supercap, battery. And actually, since we are in charge of our design, this is really our expertise, IC design, we can help you to integrate the AEM, but also you can customize it or discuss new feature, adaptation, anything which could be interesting for one or your application. Looking a bit deeper on how the AEM behaves, its modes, if we start from deep sleep mode, so really discharge nodes, and let's say light is coming and we have our cold start condition fill out, 3 microwatt, 380 millivolt, the AEM will wake up. It will start charging its internal voltage, which is called VBUC. So in the wake-up mode, it will first charge VBUC to 2.2 volts, and after that, it will start charging and it will really start managing from the source to the storage the energy, rising the VBAT voltage to V charge ready. As you can see on the left, you have three different levels: V over discharge, V charge ready, and V overcharge, which are defined by configuration. As soon as we achieve the V charge ready, we will enter in what we call the normal mode. The internal LDO will be activated and we will start living there between the minimum and the maximum levels allowed on the storage. If we achieve the maximum level, we will protect the battery and we will switch off the boost in order to get the voltage a bit down to enter back in the normal mode. If, on the contrary, we achieve the minimum level, V over discharge, in that case, we have two options. First, if we have a primary battery available and connected, we could use it to get recharge to V-charge ready, to get back in the normal mode and to have the system still be living and nothing happened to the LDO. But if the primary battery has been discharged, or if we did not connect any primary battery, we will enter in the shutdown mode. A status will rise up to inform the electronic supply that we will go down, and the LDO will be switched off after 600 milliseconds. There we will actually disconnect completely from the storage to really get it protected at 100%, and we will wait for a new cold start to happen. So we just discussed the three levels: overcharge, charge ready, over discharge, and those are defined by configuration. You can see here the table, the 7 predefined modes. You have different technology of battery and supercapacitor, and if we look at the famous Lion cell, you can see that we will charge it up to 412 voltage, and we will switch off the LDO at 3.6 volts. You can see that you have the HV out and LV out voltages defined by configuration: 2.5, 3.3, or 1.8 on HV out, and 1.8 or 1.2 on LV out. We have 3 different modes for the supercapacitor: one for a single cell charging charge up to 2.7, providing 1.8 and 1.2 on the LDO's output, and 2 modes for the dual cell, where we charge the supercap up to 4.5, and we provide either 2.5 or 3.3 on HV out. What you can see is that you always need a 0.3 drop between the over discharge and the HV out, because you have the internal drop voltage on the linear converter. If none of those custom mode, none of those modes are okay for you, you can define your own levels. You can define it using the custom mode. There you will be using 6 additional resistors. You should just, I would say, respect those 2 rules. First, the 0.3 drop voltage between the over discharge and the HV out level, and the maximum of 4.6 volts as overcharge level. If we look at the entire family, we have different products for the different sources. Actually, the harvester has different behavior. So we wanted to optimize transfer and wanted to optimize the MPP ratio, the frequency of this MPP, and the different option dedicated for the harvester behavior. So the first is the AEM 10941. Dedicated for photovoltaic sources. There the harvester behaves like a diode, and we will have a voltage ratio defined in the harvester datasheet. The AEM 2940 is aimed for thermal sources, and you actually have an external cold start circuit available, allowing you to cold start at 60 millivolts instead of the 380 millivolts required. So this is an external cold start, but it could be quite useful since a TG, so the harvester thermoelectric generator, behave mostly like a current source, providing high power at low voltage. And there it could be useful to start and to get the cold start voltage lower than 380 millivolts. And here you can start at 60 millivolts. Regarding AC sources, you could have high frequency or low frequency AC sources. If we look at high frequency being RF, you would need a matching network and an external rectifier with the AEM 3940. EPES has been designing matching network and external rectifier for some frequency, so you can look on our eval kit, you already have something that you could use for testing. But since it's external, you can also redesign it or adapt it to the antenna impedance you are using. In case of low frequency, like vibration source, inductive current, an external rectifier must be added to provide the DC voltage to the AEM. This rectifier could be a diode bridge or any rectifier using transistor, and actually on the eval kit you have a diode bridge available for testing. So I invite you to have a look on the website a bit to look at evaluation board and all the documentation available around our product. And now let's focus on some use case. Use case used with different sources. First one being the light, indoor, outdoor light. We'll see different use cases for both light and RF. So first use case will be our demo kit that you might have seen on trade show already with Chip Select. A second use case will be the product designed by Sodak for the company movement. It's actually a cattle tracker used in Australia to geolocate locality. I don't know how you call it in English, to know where your cattle is actually. We will also see an example of AGC called Jack. It's a car fleet tracker. Last example using the light is an example from Enersing, which is a PV cell manufacturer that has been designing their own product, and we will discuss the RF source with some hypothetical use case, GPS tracker working during the day and being recharged by night. So now let's look at our small demo kit that integrates sensor, humidity, temperature, luminosity, low power sensor. It also integrates photovoltaic cell dedicated for indoor light, a supercapacitor as a storage, and we have some BLE connection sending beacon messages each 10 seconds to an application that we design, working well, running on Android smartphone, and we can just see the data, and we will have a look together at how it works. But now let's open the box, see inside what we have. You will see that we have different components, being the sensor, so here in red, the photovoltaic cell here in yellow, a supercapacitor on the back, and of course our AEM 10941 that you can see on the picture, being surrounded by its passive component, 2 inductor and 5 capacitor. But how can we have chosen the size and the component around the AEM? We actually recommend you to study the energy balance. Study the energy balance starting from the consumed energy by the load over a defined period. We will here work with a 24-hour period a day. For the light, it sounds reasonable since light is coming back each morning. So we analyze and we define the energy consumed by the electronic over a day. From there, we can integrate some losses to define the energy that we must get at the boost output. We can there integrate again losses in the AEM and integrate the fact that we just have the light during the day to estimate the energy and the power source we need from the harvester. And since we know when the power is available and when it won't be available, we can estimate the energy that we must store to still supply the device during the night. Now, if we look at this study balance a bit in detail, so starting from what is consumed, we integrate the losses of the converter, could be our internal converter or an external DC-DC converter from the storage to your electronic. From the eBoost, we integrate the internal losses of the AEM 400 nanoamps and the boost losses that will depend on the input voltage, but we have the different boost efficiency curve available in the datasheet. And from there, we can estimate the energy we are looking for at the AEM input. And if we know when the source will be available and when it won't be, we can estimate the part of this eBoost ratio that we must store for later. The E-store, it could be more than eBoost if we know that during the weekend we won't have any light. So it depends on what you have been decided, but it's really important to have a look at the different energy used for your application. Let's look at a real use case. So starting back from our demo kit, we know that the average consumption is about 50 microwatts at 3.3. So this is the average consumption, even if we know that with radio communication, BLE, in that case, we have some peak current, 5 milliamps. But the average consumption to sense the sensor each minute and to communicate each 10-second beacon message is about 50 microwatts. We can estimate the consumed energy over a day, integrate the LDO losses, the AEM losses, and estimate that we are requiring 5 joule at the boost output. If we integrate the fact that we have 10 hours of light and we have a boost efficiency around 70%, since we will be working with very low input voltage, about 0.4 volt, we are looking at 200 microwatts at the PV cell output. Now that we have decided that we have around 10 hours of light, the autonomy is about 14 hours. Hypothesis, and we are looking to store 3.3 joule in our storage element that we defined as being a supercapacitor. And to store this amount of energy between 4.5 and 3.6, because as if you remember, we will switch off the LDO if we achieve the minimum level, being 3.6 over discharge level. Then we need to store this energy between the maximum and the minimum level. And to store this amount of energy, we need around 0.9 farad. So now that we know we are looking for 200 microwatts from the PV cell, we can have a look at the different technology and mostly the one dedicated for indoor light. 3G Solar has a good product that provides you around 220 microwatts under 300 lux, so very low luminosity, which should be less than what you have in your offices. The area required is about 70.5 centimeters square, and you will get enough to supply the system and to supply the electronic. If we look at the datasheet and the different specification, what you can see is the information you need to define the MPP ratio. So here they give you the VOC and the VMPP, and you just have to do the derivation to understand that you need to define the MPPT ratio at 80%. But we could also use another one, PowerFill, which is providing you actually flexible PV cell. And here this project, area about 55 centimeters square, is providing around 220 microwatts below 200 lux. Again, it's very low luminosity. If we look at 1000 lux, is 1.4 milliwatts. So it's way enough to supply the electronic we were looking for the demo kit. If now we look at the supercapacitor, well, actually you could use a battery, a rechargeable battery, and you see here different partners' name. Capix is one of our partners and provides some supercapacitor with a very low leakage current, which is actually important since all the losses you have inside the supercap must be compensated by harvesting energy. So looking at this factor is quite important. And you see the dimension of 39 by 17 by 3.9 millimeter for a 1.2 farad. We will assemble all the components, and for your information, the size of this device is 6 by 6 by 1 centimeter. And you see that we get all the data from the BLE communication on the smartphone. We see the storage element voltage rising up in the morning, staying at around the maximum all the day because we get enough from the light. And during the night, it's being supplied by the supercapacitor until it gets to the next morning and it gets back light. It gets some light back. Sorry. If we look at several days, you can see that you have the same idea of getting energy back in every day. Every day is a new cycle. And even if you have very low luminosity, we will still charge it enough to avoid reaching the minimum of 3.6 level, which would stop supplying the system, but not happening here. One word about the demo kit. We have been discussing the one with BLE communication, but actually we also have one version, the same size with another electronic adapted to communicate through LoRa. There we send messages each 6 minutes with the SF7TX power. Could be adapted to sending a message each hour with SF12. Actually, here it has been based on how, as we saw on the consumption of 50 microwatts. If the consumption change because we want to send more messages, we just have to adapt the PV cell and the supercap, but we can also extend the duty cycle if we use higher power, TX power. So this is the LoRa, I would say, version using the TTN services. And again, we have the details on the smartphone application with a small application designed by EPs. We have the same version with a 6-Fox communication. So now let's move on to other products which are not designed by EPs using EPs technology and product, but designed by some customer. First one, this one, a car fleet tracker, actually sensing if you have any shock on the vehicle, designed by AGC, and we did the small analysis using some hypothesis number, but the idea is just to show you the different options you have on the harvester and on the storage. Here we took the assumption that it was consuming 80 microwatts. We have only 5 hours of light. Let's say it's really dark winter, we just have light 5 hours per day. Loss, boost efficiency is about 90% since we will be targeting to have more than 1.5 volt at the PV cell output. If we know that we have been estimated that the source power is about 400 nanomicrowatt, we can look at X's product, which are actually dedicated for outdoor light, and we can see that they are providing way more than enough, being 900 microwatts for an area of 3.6 centimeters square. On the datasheet, you can again find all the information to define the MPP ratio, and you can see that they are providing you some number below a 1 sun luminosity, which is quite a lot. So I strongly recommend you that to test your PV cells once you have defined some potential harvester. I would recommend you to test them in your light luminosity, and if you have any glass in between, just to see also the impact on the performances. Regarding the storage, since we would like to store 6.2 joule, targeting 19 hours of autonomy, which is about 425 microampere hour at 3.7 volts. It's quite small. We can take some margin in case you have a lot of light someday, and you can see that you have a different footprint and cases for rechargeable battery with small capacity from 10 milliamp per hour to some 30. We mentioned that we have been choosing and we will put some PV cell in series just to get higher on the voltage and to get higher efficiency on the boost. What's the advantage and what's the drawback of doing so, and why not using them in parallel? If you put them in series, what you will achieve is a higher voltage, which could give you a higher boost efficiency. But if the cell is covered, it will impact the global current. So it will impact globally the system and the performances of the PV cell. If you put them in parallel, you will get the same voltage. But if you cover the cell, you would just impact that cell. You will just reduce the performances of that cell. So most of the time, you will see that manufacturer, they will use the single cell, and they will make some architecture made of cell in series and in parallel, not only in series, not only in parallel, but a mix of those two. But at least you can now understand what's the advantage and the drawback of doing so. Going back to some use case, the cattle tracker designed by Sodak, used in Australia. If we look inside the device, you have some GPS and a radio, a LoRa radio used to send the position information to the farmer application. It's using some PV cell. Again, it's an XIS product and some rechargeable battery. The idea is just to show you the study based on 1 milliwatt consumption at 3.3 and a 10 hours of light hypothesis. We are looking for 3 milliwatt at the input, and we are looking to store around 56.7 joule for 14 hours of autonomy. Those are hypotheses, and you can always change a bit the number and take some margin. It's just to show you the different steps. As I mentioned, they are using XIS, which is providing from 450 microwatt below 1000 lux, and at 10,000 lux, you see that you will be getting around 7 milliwatts. For the rechargeable battery, another option additional to the one we have seen just before, the one from Renata, providing you some rechargeable battery at 16 milliamp per hour to more than 60. Last use case about light is from Enersing, which is actually designing their own PV cell made of organic material. And they have been designing a CO2 sensor. So you see that they are using a 10 by 10 centimeter PV cell, providing more than 300 microwatt, and after 10 hours, 3 milliwatt. The storage element they are using, it's a Lion cell, and the capacity is between 10 and 100 milliampere. Average consumption of this device is about 85 microwatts. So now let's look at how to use and how could be used the RF, the long distance RF recharge. Here, as we discussed in the beginning, we recommend to use an RF emitter, which you can control in terms of power emitted, in terms of antenna, and also you could add some gain at the antenna. So we took the hypothesis of an application that could be recharged during the night inside some place, and we are using a transceiver emitting 1 watt with a duty cycle of 93%. It's actually following DHC recommendation 302208. We took the hypothesis of 2 meter distance, which is kind of a long distance, but actually we could do more. Here we decided to work with 2 meter and antenna with 2 dBi intrinsic gain as an hypothesis again. So now looking at the system, what is important is to actually to start from what is emitted to look at what could be supplied. So what is emitted is 1 watt 93% of the time, and we had some gain at the antenna. We of course have losses in the air. Those are the theoretical one and might be bigger or not based on what it should go through. So here is in the air. So we can estimate the received power being 436 microwatt after 2 meter. We can there estimate the energy received, since we know that we will be recharging during 12 hours. And from the datasheet of the 13940, we can look at the efficiency from the antenna to the storage, which is providing, as I said, in the datasheet, and is provided using our matching network and rectifier. That could be redesigned, but those are the efficiency you will have using our eval kit. So when receiving minus 3.6 dBm, the efficiency is about 43%. So we know that we will be actually from the 80 joule storing 8, from the 18 joule we will be storing 8. We will also remove the losses in the converter, and we can estimate that we have around 7 joule available after 12 hours of recharge. This 7 joule means 162 microwatts average consumption. And if we compare it with a case supplied by a non-rechargeable battery, we could estimate the size of this battery required if we are looking at the 5 years lifetime. This is about 2 ampere hour at 3.7 volt and 5 ampere hour at 1.5 volt, which could be quite bulky. If you would like to do this energy balance for your own case and own product, the first question you should ask yourself is, what am I willing to supply? What sensor, what radio do I need? How often do I need to communicate the information? Does the application need to be running all the time or just part of the time? What processing am I looking for? So it doesn't have to be that number. It could be just an idea, just to estimate the energy consumed. Also, it's important to know what supply voltage you do need to see what converter could be used if you have any current peak. And of course, asking where the application will be working, what source is available, when is it available, do you have any mechanical constraint related to the size of the device or the location it will be. And the autonomy, of course, because this will actually define the energy you will have to store, and there define the size of the storage element you should use. You could also ask yourself, do I need a primary battery? Is it necessary? Is it mandatory? Those are the different questions that are really good to start with in order to use energy harvesting. As soon as you have done this small energy balance, where we can always help you, of course, and you have decided and choose some potential harvester storage, then you can always use an eval kit from EPs to test the system, supplying your sensor, microcontroller, radio, any already existing product directly from the HV-out, LV-out connector. So we achieved the end of this presentation. I hope that you better learn our AEM product and how to use them in your application. Do not hesitate to contact us or look at the website, or if you have any question, then we can address them now. And thank you for your attention. Thank you for staying with us.